Welcome back, everyone. We're back here at hack.summit. It's 4 p.m. Pacific time. We've got 2 more talks happening today, and this one's going to be very special. It's from Chris Richardson. Now, Chris Richardson is a very experienced developer and architect. He's a founder of Cloud Foundry, which was acquired by SpringSource in 2009. He's also the author of the book POJOs in Action, Plain Old Java Objects in Action. He's also a Sun Java champion, which is a very difficult to obtain kind of title as being a very top-level expert in Java. He's also the organizer of the East Bay Java Users Group, and he's the founder of Component Systems, which BEA acquired back in 1999. So we've got a serial entrepreneur, multiple acquisitions, plus is still a hardcore developer and gets his hands dirty. Very rare combination. Chris, thanks for being here today.
Great, thanks, Ed. Thank you. Thanks to everyone who is joining in. So let me just share my slides, and hopefully everyone can see the slides at this point. So goal over the next hour is to talk about my experiences building kind of an application using what for me was quite a different kind of architecture. So namely one that's based on microservices with some frameworks or architectural patterns called event sourcing and CQRS, and then a totally different and new deployment mechanism, namely Docker, which I'm sure most of you have heard about because it's sort of getting a tremendous amount of attention these days. So that's the goal, and there's a little bit of Scala in here, though that's secondary, a little bit of functional domain model stuff as well. But the essence is microservices, event sourcing, CQRS, and Docker. So before I get into that, a little bit about me. So I actually got my start off in programming back in the 80s, programming in Lisp, building Lisp systems, compilers, runtimes, tooling, IDEs, and the like. And then eventually, obviously, I ended up in the world of Java, and then back in 2006, I wrote the book POJOs in Action, which was all about building Java applications with Spring and Hibernate, which back then were these radical new technologies. And then a little later, I started using what was at the time this obscure service called Amazon's Elastic Compute Cloud. Kind of, it's very, little known. It's sort of 2007. That turned into an open source project, which then turned into my startup Cloud Foundry, which was then acquired by SpringSource shortly before SpringSource was acquired by VMware. And there's this lovely diagram of the 3 fish that appeared in the register. But sadly, Cloud Foundry was much more of a plankton than a multi-cell organism, at least in terms of market cap. So in these days, I'm working on a couple of different startup ideas. And I'm also doing consulting, helping organizations use modern software architectures in order to become more agile, more successful. And I've also created the site Microservices.io, which is sort of a site, a resource to learn about how to use microservices. So that's me. Here's the agenda. So I'm going to begin with talking about why build event-driven microservices. Why is this particularly relevant? And then dive into event sourcing, which is a particular way of doing event-driven applications that I found especially useful. And then just talk about CQRS, which is a way of doing queries in an event-sourced application. And then I'm going to finish up by talking about building and deploying microservices using Docker. So that's the talk: events, event sourcing, CQRS, and then Docker. So okay, first up, why build event-driven microservices? So imagine that you're building a banking application. And I apologize in advance if any of you are actually working on banking applications, because my example is by sort of real world standards quite trivial. But you can imagine that in your domain model for banking, you'd have a couple, you'd have entities like an account, and an account would have a balance. It would have open operation, have an open method. It would have debit and credit methods for adjusting the balance. And then in order to create in order to transfer money from one account to another, you to create a money transfer object specifying the from account ID, the to account ID, and the amount of money that you want to transfer. So here's kind of an incredibly simplistic domain model. And then in terms of, well, what would your application architecture look like? Well, you'd have a presentation tier which implements the banking UI. You'd have various services or modules, such as accounts for dealing with the account side of things. You'd have another module for dealing with money transfers, a third module for dealing with customers, and so on. So you'd actually have a nice modular architecture. And you perhaps use Spring Hibernate, or this could be a Ruby on Rails app, of course. But and then what you'd go do is package that nice modular architecture up as a single monolith. So if you're in the Java world, you'd package it as a single WAR file, and then you'd run it on a container like Tomcat, and you'd have a relational database in the back that acted as the system of record. And this, for me, was pretty much the standard way of building enterprise Java applications for quite a few years. And there's good reason for that. So number one, it's actually just simple to build apps this way, right? They're simple to develop, they're simple to test, and they're simple to deploy. And if you need to scale them, and also with a relational database, you've got ACID transactions, and that's a nice simple programming model. And then if you want to scale these applications, well, you just run multiple copies of Tomcat behind a load balancer, and you can deal with increased load. And it works well. I mean, we've been successfully building the applications this way for a number of years. The trouble is with this approach is that it doesn't really scale to large applications or large loads. So you can imagine, over many years, applications just tend to keep growing every day. Each developer's adding some number of lines of code, and then a few years later, you've got this incredibly large, complex application. And that has a whole host of problems. It intimidates developers. You just got a massive code base, complex build system. People can't find their way around. Tends to be an obstacle to frequent deployments. In this day and age where we want to deploy an application many times a day, if you've got this multi-100,000 line application or 1 million lines of code that you can only deploy in one go, you've got all your eggs in one basket, which requires lengthy QA cycles and just slows you down. Tends to overload your IDE. More lines of code you have imported, the slower your IDE is. It slows down container startup times, which slows down development. Tends to be an obstacle to scaling development because you really want to break up a large engineering team into individual sub-teams where each team works on a specific module. So you'd have the UI team, the account team, the money transfer team, and so on. But if at the end of the day they all have to package their changes together, then there's an awful lot of coordination and communication required to get that monolith, to get their changes deployed. And then also, from a technical perspective, different modules can have very different scaling requirements. You can have a CPU-intensive module, and then you might have a memory-intensive module, but if you actually have to deploy them together, you can't scale each one optimally. And then also, lastly, but sort of more important, which in a way is a major driver here, a monolithic architecture typically requires a long-term commitment to a technology stack. You're usually stuck with the technology choices that you make at the beginning of the project because it's simply too costly to then go and rewrite to use a different technology. So, monolithic applications work well when they're small, but eventually it gets painful. So the solution, of course, is to use a microservice architecture and functionally decompose your application into multiple standalone, independently deployable and scalable services. So we might have an account management service, we might have a money transfer service, and each one of them has their own database, and they can just evolve independently of one another. They can be scaled and deployed independently, and so on. So that's sort of the solution to the large monolith, and just many companies have gone this route. They get to, their monolith gets to a certain size, and then they have to break it up into microservices. Amazon, eBay, Netflix have all done this. Another problem you run into sooner or later are limitations of the relational database. There's lots of issues around scaling relational databases. They tend to only scale vertically. You can't really scale them out horizontally. Building a multi-master distributed, multi-data center distributed data infrastructure is quite tricky to do with off-the-shelf relational databases. Doing schema updates can be problematic. You can have tables so large that to add a column which touches every row in some databases is incredibly time-consuming. It can easily exceed your maintenance window. And then, of course, there's the obvious OR, object relational impedance mismatch, where you have a challenge mapping your rich relational model with inheritance and relationships, the object model, to your flat, simplistic relational schema. And then relational databases have a problem dealing with semi-structured data in an efficient way. So the solution there, of course, or to solve many of these problems, is actually to use some kind of NoSQL database. So if you need text search, you could use Solr or Cloud Search or Elasticsearch. If you're storing graph data, you could use Neo4j. Or if you need a highly distributed available database, then perhaps Cassandra is a good choice. So it's quite common to use some kind of NoSQL databases these days. And you can easily imagine an architecture where different modules of your application use different kinds of databases depending on what they're trying to do. No one-size-fits-all kind of approach. So you've got this polyglot persistent architecture. But then, of course, we sort of actually with both microservices and then with NoSQL databases, we actually end up with problems around data consistency. So with microservices, where we've actually split up the application and split up the database, we now have a problem implementing business transactions, such as the money transfer transaction, that needs to update data that's owned by multiple services, because we need to update the from account, the to account, and also the money transfer. And that's difficult to do without two-phase commit. And then you find that in some situations, you might actually have to replicate data from one service to another, and doing that reliably without two-phase commit is a problem. So it's sort of a typical thing where we're solving the monolithic problem by breaking up our system, but now that introduces a distributed data management problem. And we have similar problems with relational databases as well, where they tend to have a very limited transaction model. So actually implementing something as simple as money transfer, where we need to update two accounts, is actually quite difficult to do with a NoSQL database. They don't have two-phase commit. You can't update multiple rows. Then also, because they have limited querying capabilities, then you tend to have materialized views, which then need to be kept in sync with the kind of the master table. So once again, it's distributed data management problem. And the solutions to both of these problems is typically to use an event-driven architecture. So namely, if microservices publish events when they change the state of some entity, and then other microservices can subscribe to those events and keep their data in sync. And you can use it to implement, as I'm going to show, these sort of eventually consistent workflows, such as money transfer, where instead of having one transaction, you have a sequence of transactions where each transaction changes the state of one entity. So here's an example of how that would work. So we do a money transfer, creates a money transfer entity, that publishes a money transfer created event, the account service subscribes to that, does the debit, publishes an event to say that it's debited the account, which is consumed by the money transfer service, which records the fact that the from account was debited, publishes another event, which then gets consumed by the account service, which credits the to account, which publishes another event, which is then consumed by the money transfer service, which then changes the state of the money transfer to complete it. So by having this event-driven workflow, we're able to update multiple entities in different databases without using two-phase commit. But of course, this turns out to be quite tricky to do, because in order for this to work, we have to atomically publish an event whenever a domain object changes. And it sounds simple, but it's not, because number one, you have a problem of, well, how do I publish events? So we could sort of do this at a low level by having database triggers, for example. Whenever we change the database, we publish an event. But that's sort of tricky to do, doesn't work too well with NoSQL and so on. Also, the changes to the database are quite disconnected from what's happening at the business level. And the physical table model is, many layers below kind of the conceptual business model. And then the other problem, and another option is to actually do event handling code, have event handling code intertwined with your business logic code. Challenge you have there is that you're sort of tangling set different concerns together. It's also unreliable. If you forget to publish an event, then you kind of you've got a bug in your program, which can be quite tricky to detect. And then also there's an issue of atomicity. You need to update the state of some entity and publish an event, and you can with a message broker. But then, the normal way of doing that is with two-phase commit, but we're trying to avoid that. And then one approach is to use a data store as a message queue, but that's sort of got a whole bunch of downsides as well. So it ends up being kind of a tricky problem, which is actually how I end up being really interested in event sourcing. It turns out that this is an excellent way of building event-driven systems that with the necessary properties of being able to atomically change state and publish an event. So let's have a look at that. So the big idea with event sourcing is for each domain object, or in domain-driven design speak, for each aggregate, we explicitly identify the events that change state. So in the case of an account, it would be the account being opened, it would be the account being debited, the account being credited, etc. And then we define event classes. So we're explicit in our domain model. Before they might have been implicit, now we're doing that explicitly. You can imagine similar events for a shopping cart: item added, item removed, order placed, etc. And then this is where it gets quite interesting. So the big idea with event sourcing is that we no longer persist the current state of an entity. So in this case, we've got an account number 101 with a balance of 405. You'd normally have that in a database table somewhere. Instead, what we do is actually store the events that have caused state changes for that entity, it being opened, it being credited, it being debited. So we're storing the changes rather than the actual current state. And then, in order to reconstruct the current state, we would load the events for that entity and then replay them. So if we did that, we'd actually, we'd actually compute the new balance. So it's somewhat analogous to, when you log into your online banking, you see a whole series of debits and credits, and then at the top it's showing the current balance. And it's quite incredibly likely that the bank never stores the current balance. It really just stores the sequence of transactions and uses that to recompute the current balance. So kind of current state is this secondary derived piece of data, and what's primary is the sequence of events. So that, and it's sort of like, well, how does that help? Well, what's interesting is before you had to update state and publish an event, and those were two things that needed to be done atomically. So that hence the need for two-phase commit, which we're not going to use. Whereas now, effectively, we have one thing. We just persist events. which kind of then implies that they get published as well. And that's one thing that can then be done atomically. So from an implementation point of view, it's a lot simpler. And also from a development point of view, it's a lot simpler as well. So in terms of, if you look if you look at my application code, so this is some Scala. So I've got some various base classes. So there's a base class called aggregate that has an apply event method that takes an event and gives you back the current, an updated entity. So I've got a functional immutable domain model, and then I've got a command processing aggregate that actually takes a command and gives you back a sequence of events, which can then be passed into apply event to compute the new state. And then, for an account, it kind of looks like this. Account deals with various commands like being opened, which turns into an account opened event. Credit a command that turns into an account credited event, and so on. And like for debits, there's an overdraft check as well. And then here's what the apply method looks like. So if it's an apply event, then it returns a copy of the object, or if it's an opened event, it returns a copy of the object with the balance set to the initial balance, and likewise for the debit event. So a little bit of details there, sort of not too relevant, but at a high level, what matters is the way requests get handled in the system. So imagine an HTTP request comes in. We want to update an entity. We ask the event store, give me the events for this entity. We instantiate a brand new account. We then apply all of those events to reconstruct its current state. We then take the command, which was built from the HTTP request, and tell the account to process it, which generates some new events, which then get persisted in the event store. So very different flow of processing of request handling. But then where it gets interesting, of course, is that on the other side, you can have other services subscribing to events. And then when an event is published, they get notified, and they can do things like update some other aggregate or update a view, which I'm going to talk about in a little while. So that's sort of the big idea, where all of the processing in your system is ultimately driven by requests from the outside world coming in, turning into commands, which turn into events, which then trigger other updates to be performed. And you might be wondering, well, I've got an account and it's been open for a really long time. That's an awful lot of transactions to load from the database each time. And the solution there actually is to periodically create snapshots. So basically it's like a memento pattern where you save the current state of an aggregate, and then in order to reconstruct the current state, you find the most recent snapshot and then find the events that happened after that snapshot. And then so you're not looking back as far in time and are dealing with fewer events. So that's kind of a useful optimization. But it turns out, in a lot of cases, you can efficiently load quite a large number of events. It's sort of, from a sort of I/O perspective, it's it's fairly efficient. So the actual API that my event store using has like a save method that's for inserting a new entity. So it actually takes the entity in the events, an update method that takes like the current entity version and the sequence of events, a find method, and also a subscribe method that's used by services that want to subscribe to the events that are being published. Whole bunch of benefits to using this approach. Number one, from a sort of business perspective, you got this built-in, absolutely reliable audit log. This series of events that are getting published actually is an accurate record of what's being done in the system. It's quite different than if you have ad hoc auditing code where if someone forgets to record a user action, the business logic is still going to work. It's just that the audit log is going to be wrong. Whereas with this, the events are the core of the business logic. It actually enables temporal queries. You can ask what is the state of the system or state of an entity at a given point in time because you've preserved all of the history. And the fact that it's publishing events fits in with today's big data predictive analytics, because those events that are coming out of the event store can go into your analytics engine as well. And also the fact that you've just preserved everything that's ever happened in your system, you can actually kind of then implement new requirements but in a way as if they've always been in the system, which is quite handy. There's a bunch of technical benefits. It solves all these data consistency problems around that you get with microservices and NoSQL. It lets you implement these event-driven, eventually consistent workflows. And it also eliminates the OR mapping problem because all we're doing is persisting events, which is a really sort of trivial kind of thing to persist, unlike trying to persist an arbitrary graph of domain objects. So that's quite nice. You know, there obviously are a few drawbacks, right? It's weird and unfamiliar. You know, we're used to persisting current state, maybe with an OR mapper. This is obviously quite different. Sometimes if you pick events, you know, you design your events wrong, that's a problem because you have to deal with that. Because the events are immutable, you kind of have to deal with that forever. So, you know, I kind of jokingly call it a historical record of all of your bad design decisions. What's nice is that the events tend to be very much tied to the problem domain, so they tend to be quite stable and quite straightforward to design accurately from the beginning. But then there's other issues like handling duplicate events. So in any message-driven system, one problem is detecting duplicate events. So you can do things like just keep track of the last processed event ID and discard earlier ones. And also in this model, the view of the data is eventually consistent, which sometimes can actually, you actually have to add extra code into your application to deal with situations where it comes across inconsistent data. You know, one of the nice things about the ACID transactions is you get consistency. The trouble is there's the cap theorem, and so at scale you just kind of have to go eventually consistent either. And then another problem is the event store, as I've described it, only supports primary key-based lookups. So, and later on I'm going to talk about, you know, the solution to that actually is CQRS, and I'm going to describe that in a little bit. So that's the big idea with event sourcing, persisting events, and rather than the current state, and replaying events to reconstruct the current state. So I want to kind of dig into a little bit and sort of kind of relate that back to microservices. So sort of in my application, microservices sort of basically contain one or more domain objects or aggregates, and for each domain object there are adapters that take inbound HTTP requests or possibly requests coming from a message broker. Those requests get turned into commands, as you saw, which then get turned into events that get persisted in the event store and then ultimately consumed by other services. And then at the same time, a given microservice is subscribing to events via this sort of an adapter that subscribes to some events, turn them into commands that update the aggregate. So that's sort of the basic building block of these microservices. And one microservice could easily contain one aggregate, or it could contain multiple aggregates, depending on how the sort of modularity of your application kind of makes sense to you. You know, here's some code. Here's a Spring MVC controller that's taking an HTTP request and invoking a service. The service is written in, you know, it's all Scala, and they've got this handy little DSL that lets me very concisely specify to transfer money, create a money transfer entity, and have it process the create money transfer command. And under the covers is actually instantiating the money transfer entity, processing the command, applying the events, and then persisting them. So that's sort of encapsulated. And then the money transfer aggregate looks like this. It's got the apply event and process command methods that we saw earlier. And then on the other side of things, it actually has to subscribe to events. So here's the handler for account debited events. And using a mini little DSL again that's saying, find the existing entity whose ID is specified by the transaction ID attribute of the event, and have it process the record debit command. So once again, it's processing the command, applying any events, and then persisting them in the database.
Looks like we may have lost Chris there temporarily. His internet may be down. We'll give him a few minutes to reconnect here. In the meantime, assuming that he is down, I will go into a little bit of chat myself about maybe some of the best practices that I've kind of learned over the years, just to fill kind of some airtime until he returns. So sorry about this delay. You know, the internet sometimes does this. So we'll just adapt and work through it. So, as soon as Chris Richardson gets back, we'll resume our talk on microservices. In the meantime, let's see. Why don't I talk a little bit about kind of some best practices for starting a business based on software or based on open source. I think that might be an interesting subject for us to talk about while we wait for Chris to return here. And so, I kind of agree with the BitTorrent founder, Bram, in that it's better to kind of get experience in a startup early in life rather than later in life. And one of the reasons for that is more of a practicality kind of reason. You know, as you get older in life, there's more liabilities. You'll have, you know, family eventually later in life. It'll be financially more difficult for you to start a business. And so ironically, one of the better times to actually embrace the risk of startups is actually earlier in life, when you have less to lose, and which is kind of a weird way of thinking about things, because when you're young,
so that it can support any queries that need to be executed.
Chris, let me interrupt
and
you
that
for a second
works
here.
Quite well.
You disconnected for just a minute there. I just want to let you know that there was like a little internet outage there. But I'm going to let you resume for kind of, maybe you could just start on where a nice break might be here.
Oh, okay. Yeah, you know, it's funny. I had a Comcast glitch.
Oh, don't worry about it. This is reality, what we live in here. The internet's not perfect. There was a giant DDoS attack earlier today that hit us as well. So, you know, we're just doing the best we can. So keep going here.
All right. So am I still sharing my screen?
No, it's just your face right now.
Oh, okay.
I'd say we lost about 2 minutes of your talk there. So maybe go back 1 or 2.
All right. Yeah, I don't want to cut Comcast too much, but good job I have some kind of dual WAN capability. It did some kind of failover. All right, so yeah, so let's imagine that you're implementing a screen that needs to display accounts and its transactions. In order to do that, you know, you normally do some kind of join between accounts and money transfers, but the event store doesn't support that. It's purely primary key based. Of course, that's where command query responsibility separation comes in. So that's like a key architectural pattern that you often use with an event sourced application. And the big idea with command query responsibility separation is, as the name suggests, you actually have commands are handled by a very different part of the system to that part of your application that handles queries. You actually separate responsibility for handling updates and reads rather than combining them together as we would traditionally do. And what ties it together, of course, is events. So as things are changing on the command side, you're publishing events via the event store, which are then getting consumed by the query side, which maintains denormalized views that kind of optimally support what the UI needs. And so we're just synchronizing both of them via but via the event-based mechanism. And so from from a microservices perspective, it looks like this. So you have a view store, which could be Mongo, which is quite good because it's storing JSON documents, or Neo4j for doing social graph data, or Cloud Search or Elasticsearch for doing text search. So you have some kind of view store. You have a service that's actually consuming events from the event store and updating the view. And then you have a query service that's basically handling HTTP GET requests by querying the view store. So we've kind of got a couple of different new flavors of microservice. So we've got the command ones, we've got view updaters and view readers or view queryers now. And so in one of the demo applications, which I need to publish on GitHub, I'm storing an account and its recent transfers as MongoDB documents. So in order to support the UI, I just need to retrieve this document by ID, and that's a chunk of JSON, which can then just get passed to my AngularJS client. And that's really quite nice. It's really super efficient versus having to do sort of complex joins and the like. So it's a nice scalable approach. And I've used different kinds of views. So for instance, Cloud Search, big fan of that. Though it sort of has pros and cons, but it's a nice hosted text search engine. So whenever entities change in my system, I've got a service that's actually subscribing to those change events and re-indexing them in the database. And then also using DynamoDB as well. So in this sort of similar way to using Mongo, I'm using Dynamo, nice hosted NoSQL as a service. And that has tables or views that support the UI. So a bunch of drawbacks, of benefits and drawbacks to this, right? It's necessary in an event-sourced application because that's simply because event stores only support primary key lookup. The notion that you've separated concerns into the command side and the query side tends to simplify each and lets you have views that are optimized to support the specific UI that you need to implement. And it tends to improve scalability and performance. Obviously, there's a bunch of complexity because we've now got a view that has to be synchronized. There's some potential for code duplication. And of course, as with MySQL master slave replication, there's actually a replication lag where an entity changes on the command side, and then eventually, as in like milliseconds later, the query side gets updated. And so, sometimes your application is a little more complex to deal with those inconsistencies. But on the whole, it's worked quite nice. Okay, so we've looked at event sourcing, we've looked at CQRS. I want to finish up by talking about how all of this ends up getting deployed. So, my application architecture looks kind of like this, where in the front, I've actually got an API gateway, which acts as like the gatekeeper into my application. That's written using Node.js. I've got a bunch of services that are implemented using Scala and Spring Boot, which I'm a big fan of, and they're all based on the event store. And then I've got various other services that are such as an event archiver that's saving all of the events into S3, as well as an indexer that's updating AWS Cloud Search. Now, each one of these is actually deployed as a Docker container. If you haven't heard of Docker, it's this excellent, super lightweight container technology that basically is sort of virtualization at the operating system level. So I've got a pipeline for each microservice that builds and tests each microservice in the usual way, JUnit test and the like. And then I actually package each application up as a Docker image, and I test that. I launch the container, and then just sort of ping it to make sure that it's properly configured. And then I deploy the Docker image to a registry. So everything, which is the central place where all of my different versions of all of my different containers are stored. Here's the build script. So it actually just moves the jar into the right place, and then runs the docker build command. And unlike, say, building an AMI with Packer, which can take minutes, actually taking a jar file and building a Docker container, which contains like every self-contained, ready-to-run version of my application, only takes about 5 seconds. So it's incredibly lightweight. And then I just run a smoke test that just basically uses the Docker daemons REST API to actually launch the container. And then I just ping the health URL just to make sure that the container isn't completely broken. So the testing's quite straightforward. And then the final step is actually to just publish it, which is doing a Docker push. So it actually uploads that Docker container to the registry, and that takes 25 seconds. So it's like 5 plus 25, 30 seconds, and I've got an app that's in the registry ready to download into my production environment. And what's really interesting is that the whole build environment is itself comprised of Jenkins and Artifactory, which are themselves running inside Docker. They're themselves Docker containers running on top of an EC2 instance. So I'm using it's kind of like Docker on Docker in a way. And that was great. I mean, when I was getting set up, I was actually able to develop the Docker container stuff on my laptop, and then just kind of then take that and literally move it and run it on EC2 instead. And then my actual production environment right now, because it's sort of minimal number of users, is actually a large EC2 instance running Docker, and my deployment tool right now is a Python script that looks into Jenkins, sees what Docker containers have been built, looks at what's running inside on the EC2 instance, decides what needs to be upgraded, and then just SSHs in and issues the Docker commands to pull down from the registry the new version, stops the old version, launches the new version. So it's brain dead simple deployment. One day, of course, I'm going to need multiple instances, and then I'm going to look at Docker clustering solution. And I'm very excited about Amazon announcing the EC2 container service, so they're just going to support Docker as a first-class service. And most likely I'll use that, but I might also look at Kubernetes or Marathon and Mesos and so on if the container service doesn't do exactly what I want. Still in sort of preview right now. Okay. So that's pretty much my talk. So in summary, event sourcing solves key data consistency issues that arise when you're using microservices, or if you're using some kind of partitioned, functionally decomposed SQL or NoSQL database. And then you want to use a CQRS with event sourcing to implement the materialized views that support queries. And then Docker's a really, really good way to package applications. So I hope that you found this useful, and here's a few links. So obviously my Twitter handle, my email address, Plain Old Objects is actually my blog, where I recently wrote an article about using Docker to package up Spring Boot applications, and so it's kind of got a little intro to Docker. And then also the Microservices.io website, where you can learn all about microservices. So I guess we've got a bunch of time for questions. So let me go back over.
Great job, Chris. Incredible, incredible presentation.
Great.
Very, very in-depth.
Thank you.
It's perfect for our audience, so thank you.
Great.
So let's just jump into the first question here. Actually, I'm just going to kind of just make sure that our audience is up to speed on everything here. I would love to hear from your perspective what you think the list of advantages are of using Docker. Like, what would a company get from using Docker out of the box? Because if you look at the polls here that we've asked, 33 people have said no, they are not using Docker at their company, and only 3 people have said that they are using Docker. So maybe you could go over the value proposition in terms of the concrete benefits to users.
Oh, yeah. So, I mean, it's actually a really, really interesting issue. So the way I look at it is, so a great way of deploying an application is to package it up as a self-contained thing, right? So effectively, containerization in some sense, right? so that whoever's deploying the application doesn't have to be concerned with all of the intricacies of, well, this app needs Java 7.xyz and Tomcat this and so on. So you kind of want to, you sort of want to package it up as a black box that abstracts all of that away. And so, if you look at, say, what Netflix do, they package their applications or their services up as EC2 instances, right? And that's actually really good because EC2, AWS is this great infrastructure for running EC2 instances. You have auto-scaling groups and elastic load balancers and all of that technology that's designed to support EC2 instances. The downside is that EC2 instances are actually a very heavyweight containerization mechanism. Building one can take minutes. Actually booting one can take minutes. Whereas Docker has many of the advantages. You package something up as a container, and it's a black box, and it doesn't matter what's in it, whether it's Java, Ruby, or Node or whatever. From the outside, it looks the same, but it's super lightweight. So it's 5 seconds to build a Docker container. It's kind of like 20 seconds or 30 seconds to upload it to the registry, another 30 seconds to pull it down from the registry, and then the startup time for a Docker container is basically the startup time of your application. You don't have to boot the OS, for example. So from the moment my app is built and tested to running in production is like kind of, what's that? Do the math, minute and a half, right? It's really quick, really cool.
And I would actually add to that and say that the industry support right now for Docker is unprecedented. It seems like most major API and technology companies are kind of jumping on board the support for Docker bandwagon now. Which
absolutely. The downside,
very universal standard. And by the way, real quick, can you just stop the screen sharing because we can't see your
Oh, sure, yeah. The downside actually is that Docker can. The support, the paint isn't really dry on all this Docker container infrastructure, right? It's still kind of early days. Whereas say elastic load balancers and auto scaling groups have been around for a number of years, right? And it's just sort of super mature technology. The Docker kind of support is, it's still work in progress.
Makes sense.
But it is remarkable that a year ago Docker was this obscure little thing, right? I think it was about a year ago. I remember driving to a Docker meetup in the rain, so it must have been about November. And now it's like this huge phenomenon.
Oh, it's enormous. I mean, kind of a very similar trajectory to Apache Spark, actually, in terms of the.
Yeah, it is. Yeah.
And we'll be hearing from the inventor of Apache Spark a little bit later in the week. So let's go ahead and jump into some of the questions. Scott Davies is actually asking the first question with the most votes. So Scott will win the lottery for a free mentoring session with a participating speaker of his choice as part of hack.pledge, which is an initiative for developers to help mentor each other as their 2015 New Year's Eve resolution. And you can learn more about that in the Get Involved tab. So Scott's question is, what do you think still represents the biggest challenges in developing and running a microservices-based architecture?
Yeah, I think that sort of the number one thing is complexity. Multiple levels, right? On the one hand, so you look at the development experience, right? In a monolithic application, you have a single code base. It's all sucked into your IDE. You could make changes to any part of it, and that's great, right? Whereas in a microservice app or in a distributed application in general, you've got multiple code bases. There's RPC or some other remoting mechanism between them. So you've sort of gone from regular method calls, function calls, to RPC or messaging of some kind. So it's just, and actually just your day-to-day experience can be more complicated. So that's sort of the development time. I mean, there's a whole bunch of other things as well, like testing, right? So I can test my. I mean, for years I wrote test scripts that would launch my application and then test the UI with Selenium, right, or some other GUI testing tool. That was kind of nice, but now imagine you've got a whole, you want to test a service that actually depends upon 10 other services. Suddenly, all of those services have to be present. So there's sort of complexity there in writing your tests and orchestrating the startup of of what it depends upon. And then likewise in production, with a monolith, you take your monolith and you copy it onto a server and reboot the application, restart the server, and you're good to go, right? Now, you've got many microservices, all these different moving parts which have to individually be monitored and managed. If a fault occurs, right, and it's service A is reporting an error, maybe it's with A, but maybe A is calling B, maybe the problem's with B, or maybe it's with C, or so on. So actually drilling down, imagine filing a trouble ticket, right? A is not working, and then the A team looks at that, sees that it's service B's problem, and then reassigns the trouble ticket to B. And so it goes on, and 10 levels deep, you've got this trouble ticket bouncing around, so even fault resolution can take a long time. So it's sort of like overwhelming. There's just everything is actually more complex. Except, of course, if you're having to deal with a massive monolithic code base, then that you're in a different world of pain. And then, I need to make a change to one small module. Well, that's going to take a long time. Whereas in a microservice architecture, I've got one little change. I just kind of like make the change, push the code, and it's tested and deployed. So it's sort of, for smaller apps, there's a lot of complexity that may or may not be worth it. But for larger apps, the pain of a monolithic code base tends to outweigh any downsides of complexity.
Okay, great. Thanks. All right, next question from Aaron Held. The biggest challenge that I face is implementing role-based access controls across microservices. What do you think is a desirable pattern? Using a proxy with an OpenID connect seems the best, but it doesn't feel elegant. What do you think?
Yeah.
And maybe before you answer that, maybe you could kind of rephrase the question in maybe simpler terms that audience members who are not too deeply familiar with microservices yet might first understand before you dive into the answer.
Well, yeah, I mean, it's sort of it's kind of like, well, I mean, I look at it like, how do you handle security, right? Because let's imagine in a monolithic application, once the request enters your application, it's like inside your JVM, right? So if a method gets invoked, it can actually trust, it knows that it's not being called maliciously, right? Because it's effectively it's inside the JVM. Also, the identity of the user is passed around as a thread local, so if anyone wants to check, they can, right? You got this whole security context. In a microservice architecture, so a request comes into service A, which can then turn around and call service B. So then it's like, well, B gets a request. Does it really know that it came from A? How can it sort of validate it and actually verify the authenticity of that request? Because you've sort of gone from inside a JVM or inside some kind of VM to a networked apps, and of course the network is sort of not necessarily to be trusted, right? So even just securing the pipe between services is, you kind of have to have some kind of sort of secure communication mechanism in place, probably SSL based, for example. And then how do you pass around the user identity? Say the front end knows but then how does sort of services that are deeper inside the system know? And so a common thing is just to pass around a token. Like, I mean, the app I'm working on, I just pass around the OAuth access token. So any service that gets invoked can actually checks to see that it has an access token and can verify it. So I think, so some mechanism like that kind of deals with authentication. And then the actual authorization, I don't know if that's really any different, right? Because you've got, say if you've got a token, you know the identity of the user, and then you can actually do the authorization check to verify that they can perform that operation. So it's fairly similar.
Okay, great. I think we have time for one or two more questions. We're just going to jump to these here. So advice for Objective-C developers when getting ready to learn Java. How do you transition from Objective-C to Java? And maybe a more general form of this question would be, just in general, how do you transition from any language to Java?
That's a good question. I mean, I don't really actually have a good answer to that other than go find a good book on it and go study a whole bunch of code that other people have written and go to meetups and just sort of immerse yourself in the community.
Now, it's not necessary to program in Java to harness microservices, right, Chris?
Oh, absolutely. I mean, the microservices can be written in whatever language you want. I mean, I just sort of happen to be immersed in the JVM world, right? So, I mean, these days, I mean, I don't really actually program in Java much anymore. I try and use Scala, actually.
Mm-hmm. Now, how would you? Now, it's very interesting because 10, 15 years ago, Chris, when we were kind of first kind of getting our feet wet with Java and J2EE and the whole ecosystem of application servers emerged, there's this whole idea of a message queue, right? And there's a lot of similarities between microservices and message queues from back in the day. What do you think the key technology advancements or distinctions are that differentiate what folks are doing today with microservices versus what could be built 10, 15 years ago with message queues?
Well, yeah, I mean, number one, right? You got a bunch of services, and they can either communicate synchronously, so they could be using REST or Thrift or whatever makes sense, or the services themselves can communicate asynchronously. And I sort of, this talk was focusing on the asynchronous communication side, and the event store itself kind of functions as both a database of events and a message broker sort of simultaneously. So that would be one point. And the other interesting thing is as such, these microservices are not anything new, right? It's really service-oriented architecture or distributed systems without all of this sort of associated craft of like WS star standards and enterprise service buses. So the concept of SOA at some level is just it's distributed systems services that are communicating. It just sort of got went down a detour of just a whole bunch of vendor-driven stuff. So it's so I think you can. Some people will just debate, well, this is just you could just argue that this is just yet another term for distributed system.
Now, there's also, this is the last question, but we have to go here. We only have a minute left. So there's the reactive manifesto, right? And reactive programming as kind of a movement and an initiative. How would you characterize microservices fitting into that? Is that an implementation of reactive programming? What do you think about all that?
Oh, yeah. I mean, number one, it's funny. Number one, I hate manifestos because, engineers shouldn't be like pro or con. Well, engineers should recognize that there are trade-offs, right? So manifestos are just sort of blind advocacy, which isn't really helpful. But having said that, I mean, the reactive programming style for situations that need it is useful. So to some extent, it's mostly an implementation detail. So you could, I mean, on the one hand, I mean, I'm talking about event-driven microservices. So there's sort of it's kind of a reactive theme, but the actual event-driven logic can be synchronous in style, right? It can use threads, and threads can block, and kittens won't die, right? So it's kind of related, but it's kind of separate all at the same time.
Makes sense. Chris, we're just about out of time here. Any parting words before we take off here?
Well, I would just encourage everybody to just read up on microservices and their pros and cons, and simply, just understand what the trade-offs are and use them appropriately. Because there are many situations where where plain old monolithic application is what you need.
Great. Chris, fantastic words of wisdom. Thank you so much for your time tonight. Really, really
great. Thank you. Just sort of encourage everyone to ping me on Twitter or email, check out my blog, etc. So, thanks.
Great. So, guys, we're going to go ahead and go to the next speaker in just a second here. In the meantime, if you really liked what Chris had to say here, please go ahead and make a donation to our coding nonprofits in the Get Involved tab, which is now highlighted for you. It should be in Crowdcast. And also, please consider signing the Hack Pledge. It'll be a great way to pay it forward and make your New Year's Eve resolution to help other developers around the world. Chris, thanks so much for your time. We'll be back in just a couple of minutes with Sarah Allen, a Presidential Innovation Fellow, co-creator of Adobe After Effects, who's going to be giving a great presentation. It'll be our final one for today. Thanks, Chris.
Thank you.